everyone. I'm Cindy San from Stanford, and along with Julia Fasaki from Rice and Angela Wu from Hong Kong USC, we welcome you to the very first seminar of the microTAStic seminar series. We are really overwhelmed by the enthusiastic response in the community. We have close to 700 people who have registered for the seminar, which far exceeds the maximum that Zoom allows us, at least for the Stanford license anyway. But thank you to our advisor, Dr. Amy Kerr, and the student organizers, Myron, Nick, Sai, Steph, and Giannis, and also our sponsors, CBMS. We were able to talk through all the logistics and be able to set up the live streaming options for those who couldn't get on Zoom today. Our goal of starting the seminar series is to really share exciting news and also to build a community in microfluidics, lab on a chip systems, and also related fields, which is a lot of them, in a more regular basis and also somewhat informal manner. And therefore, our choice of using the Zoom meeting mode instead of the webinar mode so that people can see each other and also chat. We have a very exciting lineup of speakers, as you can see on the screen here, for the next 5 months or so, and we hope that you can join us in each and every one of them. So there's some more info on the website for any updates, so feel free to take a screenshot of the slide if you want to find out more. So just a little bit about Zoom etiquette. I'm sure a lot of you are very well familiar with it by now. Please mute yourself if you're not speaking, especially during the seminar. Type your questions in chat and we'll collect them and we'll do Q&A at the end of the seminar. Please use your full name and also affiliation so that we can identify you easily, and then we're going to put instructions on how you can do that. So a few of the instructions, so make sure that you mute when you're not talking and others. So don't touch the share screen or the record button, which I don't think you should be able to if I set up the options correctly. So in today's inaugural lecture, we are very, very excited to hear from Professor George Whitesides, who is the Woodford and Ann Flowers University professor at Harvard. George probably needs no introduction and of particular relevance to this community. He's the one who makes microfluidics widely accessible as we know today by introducing soft lithography to the field, among many, many other things. George has been recognized by many awards, and it will probably take me 30 minutes, half of his seminar time, to go over the list. But I'll just name one here, which is the 2022 Kavli Prize in Nanoscience, which honors him for creating molecular scale coatings for services, which enable unprecedented control and engineering of service properties. The work has transformed service science and has led to applications shaping our daily life in areas from medical diagnostics to semiconductor devices. On a more personal note, George was my PhD advisor, and he is the reason I'm the researcher I am today. And I'm sure many of us who have trained with George felt the same way. So I'm very honored to be able to introduce him today. And George, we all look forward to your lecture.
Thank you very much, Cindy, and thank you for setting up this hodgepodge meeting. It's very attractive. I really enjoyed meeting everybody again. Okay, is this you or me? It's not me. Here, that's me.
Yeah, so just tell me advance slide and I'll go.
Okay, so we are now in the seminar, is that right?
Yeah.
Okay, so let's go. I should say at this point, just for anticipation, that most of this seminar is in SAMS and storing information, and the microfluidics is a little bit in the future. One of the things I want to do at the end of the seminar is give you a little bit of an assessment, in my opinion, of the problems that need to be solved and ways of going about solving them. So what's the future look like for this field? Because it's very interesting, but it doesn't yet have the characteristic that it's found a home. So we'll go from there. So let's have the next slide, please, Cindy. Was that me talking in an attractive female voice?
No, I think there's someone else. Go ahead.
All right. So we all know, we as chemists and material scientists know, that information storage is a enormous technology, which is enormously important. It also, we should understand, has, even though it's very well developed and represents one of the real accomplishments of modern technology, it still has a bunch of things wrong with it. And among the things that are wrong are that the cost of storing data is very large. And you say, well, how can the cost of, charging up a bunch of capacitors be a big deal? The answer is it is. So one reason one finds storage farms near rivers is that you can use the river to cool the storage farm. And all the heat comes from somewhere, and that heat is the business of keeping the medium going. It's also the case that although there are technologies that are developed that are very, very successful and very highly functioning, for example, magnetic tape, these are not really perfect because they are not enormously high density, and more importantly, the lifetime of the stored bit of information is pretty finite. And so if the objective in stored information is to find something that has the characteristic that it is really cheap, it involves really little information, little energy to keep going, so you don't have to eat or store, and it has a long lifetime. So if you put pictures of something on tape and then come back in 20 years, it's still there. I don't want to oversimplify a complicated problem because software is also pretty important and the algorithms that are involved are important. But we don't have a perfect system yet. Now, what is information? What do you actually use it for? You use it for storing text. You also use it for storing pictures. And in fact, you're told that much of the information storage that goes on stores pictures of children and pets and things like that. Just stuff that people take pictures of. And it's almost all stored on magnetic tape. And the problem with this is that if you have something like a high value storage task, storing a movie, for example, you have to go through and restore the medium because the medium itself goes to pieces over time. So you rewrite the tape into the same medium or a different medium, and that takes time and effort to do. And so at the end, I'm going to offer a little bit of speculation about what these new methods might be useful for, but let me get to that when I get to it. So what one needs is different methods of storing information. And one being what it is, if you have different methods and the different methods work, the market will figure out what they're good for. That's the great virtue of the technology or the science technology and technology product interfaces. They really straighten this out for you. And this first slide simply gives a measure of the amount of information storage that one needs. But I just remind you of this sort of obvious fact that if you look at the amount of information that's pumped down to the ground from a satellite that's taking pictures of, let's take an arbitrary place like North Korea, it turns out to be an enormous amount of information. And that I'd like to come back to in 20 years and find out if anything has changed in that period. And we really don't know how to do that right now. So there's lots of room in national security, there's lots of room in individual security, and there's lots of room in individual privacy for new methods. Now, this is an area that chemists have historically not spent very much time looking at. We certainly make the polymers that make the magnetic tapes and things of that kind, and also the magnetic colloids. But the underlying idea of are there different ways of doing things remains to be seen. And what our initial effort was was to see if we could find ways of coming up with things that were adequate methods of storing information, or even good methods of storing information, which we could use as starting points for developing a program and storing information, storing and looking at computation of stored data as we go along. And I'll tell you our progress in that. We've solved part of the problem, and there are other parts of the problem in which we've made no progress. And that's a good time to think about a field if you have a good idea, because if you can deal with the things that there's been no progress, you can really contribute to the field. So slide, please, Cindy. So these are just some background data for magnetic tape. The standard, the best method of doing things right now is still magnetic tape. And if you're interested in long-term storage, you have to recopy a tape every 7 years. I don't remember where these data came from. But you have to also provide special storage conditions so that you have to keep the tape flexible and working without cracking or breaking. And that requires careful control of temperature and humidity and dust levels and electrostatics and other things. And all of these can be critical and also expensive. And then the data centers have huge environmental footprints. And it's energy used primarily in maintaining these carefully controlled conditions for making sure that the tape continues to operate over the course of basically decades. So what one needs is a sustainable and secure and expensive archival storage data. And I'm sure that all of you read the newspapers and recognize that hacking is now basically a method of conflict for the developed countries. So this is something which is going to be more serious as time goes on rather than less serious as time goes on. And I think every big country and some small countries have very sophisticated hacking groups that are thinking about various aspects of this problem, both from the point of view of protection and also from the point of view of exploitation. And it's fair to say right now that this is just something in which we are aware of the problem. We see examples of successful and unsuccessful hacking, but it's not a stable world at this point, and it needs new things to work with. And I'm going to come back to this a little bit as we go through. Slide, please. Now, I'm going to do something here which will offend some of you, and others it will not offend. And I hope if you're among the characteristic group that's offended, you will let it go by. And if you're not offended, you might actually learn something. But the question is, how do you store information digitally? And most of what we use is you use a base 2 system. That is, we store information in terms of exponents of the powers of 2. And I'm going to show you an example of this using not bits, not capacitors, which can be either charged plus or minus, but fruit. And I'm going to do that for the sake of arguments. But if you look at fruit, 2, for example, the number 2 is 1. 1 is 2 to the 0, 4 is 2 squared, 2, 4, 8, the watermelon down at the bottom is 2, 4, 8, is 2 cubed. So that you can store all of these information, you can store any number in terms of some local exponent of these bits that you see associated with pieces of food. I'm going to show you how to do that, how to do digital storage, not because I don't think you don't know, but because it is such a crucial part of this method I'm going to show you that it's important that you get a little practice in it since it's not part of the normal chemist's way of doing things. Slide, please. So, if I want to store a bit of information, I would use a binary string. 0, 1, 0, 1, 0, 1, 0, 0 is what I have. Now, how am I going to do that in terms not of capacitors, but in terms of bits of fruit? And the answer is, if I have a 0 in the string, what that represents is, it would be in terms of fruit, that piece is missing.
So if I have a basket and the basket is a location, but the 0 would represent that I have a 0 in the first position would represent the fact that I have no cherry there, and hence have nothing that's a 1 involved in summing to give the final thing. And 2, I have 1 strawberry, I guess that is, looking at it. And so I would have a 2, and there's no peach, so there's a 3, there's no 3, and 1 apple, so there's a 4, and so on. I just go through in terms of orders of magnitude in the fruit that are involved, as the number that's given there is 2 to that exponent. Slide, please. So one can come up with a variety of different things, and what I show is simply an example there, that if I have 1, 2, 3, 4, 5, 6 different locations, and I want to, or 6 different bits of information, I want to store 6 numbers. I can store those 6 numbers in terms of whether I have or don't have bits of fruit to put in the basket. And what I show you is a series of baskets made up with bits of fruit in them, and you could, I think, go from there. But the crucial thing I think to understand here is that if I can store information in terms of baskets containing pluses or minuses for fruit, either a kind of fruit is there or it's not there, then I can store information in anything that I want to. Basically, I can use billiard balls, or I could use automobile tires, or I could use almost anything. I can, of course, use capacitors, which are either charged 1 or they're either charged +1 or they're charged not at all. That works fine at all. But all I need is a number of distinguishable things. And also, I've got all of this information in terms of powers of 2, but I can do it in terms of powers of anything, so that I can work with different bases if I want. So I could have, instead of 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, so on, instead of having that kind of method of constituting numbers, I had 3 to the 0, 3 to the 1, 3 to 2. That would work equally well. It's just not what we do, because it's not easy to come up with a capacitor that stably can occupy 3 voltage positions. So what the task is then is to find a method of easily storing information in terms of absences or presences of given things, whatever they're going to be. And that's where the chemistry comes in. Slide, please. Now, people have been aware of this problem for quite a long time. And one of the enthusiasms in the world of biology right now, and looking for new directions to go, is to think about DNA. And with DNA, you can, of course, look along a sequence of DNA, and that sequence, which is given in terms of 4 bases, also stores information. And the fact is that an E. coli has in the order of 1 billion bits of information stored in its genome. And it has various tricks that it can use to replicate or amplify or do other things with this information. So DNA looks like a good method of storing information. The trouble with DNA, everything that I've said is correct, and you can store information in DNA. The trouble with DNA is that it's hard to synthesize it. And much of the work that's been done with DNA has been done using technology that's been developed in biochemistry for other purposes altogether. And it works extremely well. Those of you who work in biology know that you can take sequences of DNA and amplify them by amplifying the DNA or by reading them off into RNA or by doing other things to them. You can do all kinds of things there. And so it all works. But the point that's the hard point is making DNA. Now, the people who make DNA, whose job it is to do that, are making some enormous steps in the right direction. So this may eventually turn out to be a route into this problem. But our supposition is at this point that it's just hard to do. And if there are easier ways of doing it, maybe that works better for one or another reason. So you can see down in the lower left-hand corner some of the problems in using DNA for data storage. It's expensive and slow to make it and to read it and write it. And there are errors in doing chemical synthesis of long sequences. And there is still an active disagreement as to how stable it is. So it's a pretty stable molecule, but you find numbers in the literature for the stability of DNA, which are, I think, based as much on wishful thinking as on some experimental measurement. And it's one of the things that needs to be worked through as we go through looking at different kinds of media for different purposes. Slide, please, Cindy. Thank you. So here's some data storage as shown here. And, you can see that although I think this relatively simple cycle represents one of the most important contributions that chemistry has made to biology, it still is complicated to do to get these things to work well. Working with phosphate esters is not straightforward. These are a series of reactive esters that have to be manipulated correctly to give bonds in the right order. And it can work. And there are a number of companies that do it in various costs and whatever, but it's not trivial to do. So one of our questions was, could we find something that was much easier than doing this kind of chemistry? And I'll show you a solution. Slide, please. So here's a method of doing things. And what one sees here is a data storage sequence, a sequence of a DNA-like molecule. It's not DNA, obviously. But you can look at this and ask, after you've assigned positions to the various locations along the strand, you can simply ask yourself, if when you sequence this, do you find something there? Do you not find something there? And if you find something there, there's a 1. And if you don't find something there, there's a 0. So it's exactly what I showed you with the fruit, the one difference being that you've got to do the synthesis and then you have to do the chemical decoding. And those are doable, but it's not trivial to do. Jean-Francois Lutz has been one of the leaders in this area, and he's done some really splendid work in this field, but it's still not easy to do. And recording information on a magnetic tape is a much more straightforward process. Slide, please. Okay. So the procedure that we used in our initial work is shown here, and I should emphasize that this work was done in collaboration with Milan Merksic at Northwestern. And he's been a wonderful collaborator, and we could not have done this without him. So Milan worked out a technique, which is shown in the upper right-hand side, by which one makes a SAM, and the SAM is terminated in an N-hydroxysuccinimide group or something related to that. And the reason for that succinimide, the reason for that is that the double bond in that 5-membered ring is very susceptible to Michael addition by SH groups. So if we take different molecules, amino acids or short oligopeptides, and we terminate those with molecules that have a cysteine, the cysteine has an SH, and the SH, if you put a drop of that material on the SAM containing plate, the cysteine adds. And what one gets then is a SAM that has a terminal oligopeptide, which is attached via this S carbon bond that we've just made. And that can take advantage of some of the technology in spotting and mixing and sampling that the people who do this kind of nucleic acid chemistry have done. And Milan has worked out very satisfactorily for working with it, and it is extremely effective. So basically what we do is to make a SAM surface, and that's straightforward to do. And then we spot it using a series of techniques that are developed by the people who do spotting in nucleic acid chemistry, which is basically to take the amount of liquid that rests on the point of a device and drips into a well. And then we can mix it. And that also is a very clever technology that works. And what you end up with is a series of spots with each spot terminated by a oligopeptide. And if you use a laser to ablate these spots, the spots when they come off can be distinguished on the basis of the terminal oligopeptide as indicated in this slide. And so what you read is the molecular weight of the oligopeptide that is on the terminal position. And from that, using various techniques, you can either get a sequence or you can just work with the molecular weight, but you get the equivalent of ones and zeros by asking, is it there or is it not there? And a lot of this works because of Milan's cleverness, but also because of the extraordinary cleverness of the people who make these commercial devices that are used for manipulating, spotting, preparing procedures or oligopeptide terminated SAMs for analysis procedures. And Milan has done a lot of this kind of thing for his own purposes, which are to determine what ligands stick to proteins and what proteins stick to ligands in biochemistry cycles. SAMD. Slide, please. So here we're going to do an experiment. Please run the movie, Cindy.
Yeah, George, let me share because I think I have to activate the sound. Okay. All right.
As the world's data storage needs grow, new strategies for preserving information over long periods with reduced energy consumption are needed. Now, researchers reporting in ACS Central Science have developed a data storage approach based on printing a variety of fluorescent molecules onto an epoxy surface in tiny spots. The mixture of molecules at each spot encodes information that is then read with a multi-channel fluorescence microscope. Current devices for data storage, such as optical, magnetic, and flash memory, typically last less than 20 years. Scientists have explored storing information using other classes of molecules, such as DNA or other polymers, but the scalability of these approaches is currently limited by high cost and slow read-write speeds. In this work, the researchers chose a set of commercially available molecules that emit light at different wavelengths. They chose to encode a seminal research paper by the scientist Michael Faraday, written on a 7x7mm area of a glass microscope slide. The molecules, however, are invisible to the human eye. The team used an inkjet printer to print tiny spots of fluorescent molecules onto a custom epoxy surface, where they became permanently attached. The tiny spots represent a string of computer code, where each bit is either a 0 or 1, depending on whether a particular molecule is absent or present. Then a multi-channel fluorescence microscope was used to detect the molecules at specific wavelengths. Custom software interpreted the images to decode the message. The information stored using these molecules could be read at least 1,000 times without any meaningful loss. According to the researchers, the strategy has a read rate of 469 bits per second, which is the fastest reported for any molecular information storage method.
So this particular embodiment is used by that illustration, uses optical detection. We've used mass detection, which uses mass spectrometry and which done primarily with Milan, and then optical detection, which Amit Nagarkar worked out in the group, which is, I think, a superior method overall. But both of them had the characteristic that they will read and write at high density and do so rapidly and allow various manipulations to be carried out as we go along, and we'll return to this. So, slide, please. Yeah, there we go. So what happens here is that instead of having different fruit, what we have is different colors of the molecules that are put on the surface. And that works in exactly a parallel way to the method that I described for the fruit. And it works extremely satisfactorily for this application. Slide, please. Cindy. Okay. One thing which I would emphasize here is that we used in this particular example a polymer surface that was designed by chemical reasoning, but the key element was that it relied on a series of dyes which were developed by the DNA community to make things work in terms of optical detection. And it's an example of something which we've tried to do throughout this project, which is to take advantage of compounds, processes, and devices which were made for somewhat different purposes, but have been optimized by the DNA community. And so this all worked very, very well because these fluorescent dyes could be obtained in a straightforward fashion. You just buy them, and we didn't have to develop them. And that ability to rely on the prior work of superb technicians developing chemical compounds, processes, reactions, devices, is done an enormous amount to simplify this particular methodology. And Amit, I think, was very clever in putting this together, and Alexei 10. Slide, please. So the chemistry part of this was just simply how do you put things under the surface, and what we used is a polymer film, which is a mixture of bisphenol A, diglycyl ether, which means that there are epoxides on it, and triethylamine, which means that the film, after you've made it, has the epoxy groups there. We react with the triethylamine, and that makes an excess of reactive secondary amine groups. And then we react that surface, once it's on the surface of the SAM, react that with the fluorescent dye, and you end up with the attachment of the dye covalent to the surface. So these systems look very stable. They're certainly very easy to make. I'll come back to how they compare to other methods as we go along. Slide, please. Now, this is one of the things which I think is a little surprising about all of this. It's still something that I have to brood about with detail. And that is that you can see that if you have a spot and you want to have multiple dyes involved somehow in the same system, that what you do is to put different colored dyes precisely on top of one another. And with that sort of registration, you can say that such and such a spot shows colors that are characteristic of these dyes. And that's very attractive. I mean, it looks like a good way of doing things. The one problem with that is that it requires registration, and you have to have an application device that puts things down specifically where you want. What we find is that if you use the procedure that I showed you, you don't have to register the spots. You can simply figure out from where the spots are on the surface, what spots go with what larger spot. And that ability to make systems in which you can make registered grids without registration of the overall array of spots is a very interesting characteristic of these systems, and one that we're still figuring out how to use. But I think one of its characteristics is that it will enable certain kinds of cryptology that cannot be done otherwise. Slide, please. All right, so you've seen the writing, and this is done using a conventional XY printer. And what we have found is that what we need to do is, in considering how to get maximum density of spots, how to get maximum information and maximum writing speeds, is we need to be able to develop a system in which we can write rapidly and have the spots close together. And this kind of system does it. But one of the opportunities in this area is going to be to develop writing systems that are faster, which means basically better XY printers. So the current systems that we have writing speeds using this methodology of 16 bytes per second. And I remember you that a byte is 8 bits. And so that depending on how long your words are, you can do the calculation you want to any way you want to. But a 16 byte per second writing speed is actually quite rapid for a chemical methodology. And it's much faster than you can synthesize DNA in sequence. Slide, please. So what we do is to do exactly what I've sketched here. That is, we have, instead of fruit, which we put in a basket to end up with a series of bytes, what we have is dyes, which we attach at a spot, and that gives us the sequence of bytes that we're interested in. It's exactly the same process, or exactly a parallel process. It's just very fast, and it works very well. Slide, please. Now, this particular method, I want to show you, although we had nothing to do with its development. It was developed by Texas Instruments for different purposes. How do we read color in these spots and do so rapidly? And what we do is to take advantage of a very clever device developed by Texas Instruments for their own purposes. And what one does, what we do here, is we take light from a laser, we shine it on the surface because it's on a gold substrate. It bounces. So the light comes out as a spot from the sample, bounces off a mirror, and goes onto a diffraction grating. And then the diffraction grating will separate the light according to wavelength. And what this Texas Instruments device has is, in place of a detector that moves, it has a series of microchannel detectors, which are separated by 10 nanometers, in the order of 10 nanometers as bandwidth per channel. And so the methodology here for detecting the sample by its color is basically to shine the system, then see where the light comes off with what intensity. So it's a method of doing spectral analysis without moving parts. You just rely on positioning many detectors, detecting elements very close together, and you end up with what you want. And it's an extremely versatile method for doing detection for nanoscience and these kinds of systems. It also works for those of you who are interested in microfluidics and other areas where we've used the same kind of thing. But it's a very good method that takes advantage of the cleverness of the people who work with DNA synthesis. Slide, please. So this is simply, I think, a movie. What we've done here is simply to scan the laser. What Milan has done is to scan the laser over the surface, and you get this kind of sample spotting. And each of these spots then becomes the basis for reading bits and bytes of stored information. Slide, please. Good. So this just gives you some examples of optical methodology. we start out with in this particular case, a slightly over 7 millimeter sample size that will store 14 kilobytes of information. And you see the image that's on the upper right-hand side, and then see it in terms of individual colors as separated out by the device that I've shown you down on the bottom there in that series of slides. So you get good separation and good color sensitivity. Slide, please. Now, one of the key elements in all of this kind of thing is how many times can you read these systems before the reading interferes with the fidelity of information stored. And I have to say the results here have been better than I expected. So what you see is the same region of one of these slides. In example A, it's read once, and this is what you see. In example B, you've already read it exactly the same region 1,000 times, and this is the 1,001st time. And what you see in number C is for the dye, how much the intensity of the dye fades on 1,000 reads. And I guess it's how much of the intensity is preserved after 1,000 reads. And the answer is most of it. So this is not a sample that leads to bleaching of the dyes. It leaves the dyes of a given color, that color, and accessible on repeated applications of this methodology to read them. Slide, please. Now, you can also use this method to work out images if you want. This is just an example case that we've done where we have taken an image of microfaraday in color, which is 3.95 kilobytes, and converted this into a binary string using technology that's been well developed in other purposes and stored it, and that's in the second image there, and then reread that second image to regenerate the picture of microfaraday, which is on the right-hand side. And you can see the overall error is very small. That is, we don't have any obvious missings. These image storage systems are very sensitive to defects in either the reading or the writing. And if there were defects in reading, you would see it in terms of streaks of nonsense, basically. And so the fact that we can do the storage, writing, and storage recovery of the image is a very good indication of the accuracy of the method, which is extremely high. Slide, please. All right, so this gives some comparison of the cost, stability, write speed, and read speed of a number of methods. Magnetic tape is, as they say, the example that's presently most widely used. DNA is these are examples which have been worked out, and SAMD is one of the mass spec methods, and fluorescence imaging is the method that I just showed you. So the cost of the fluorescent imaging is very low. Stability, it's actually rather hard to measure the stability of these systems. What we're doing is to work with Michael Fink, who was here a moment ago, and the Fraunhofer Institute in Germany, a Fraunhofer Institute, which is the standard for determining these sorts of stabilities. And they have a series of protocols which they are using, but it looks as if it is the method that I've showed you is a very good method and has long stability. The write speed is quite good. So what you're seeing there is megabits per second. So for the fluorescent method that I've just shown you, you can write about 16 times 10 to the minus 6 megabits per second, which is a good writing speed. And then the reading speed is 10 to the minus 2 megabits per second. And these are both satisfactory for everything that we're doing right now. The printer is the limiting speed in writing. And one of the things we need to do is to pay attention to the engineering of the printers in such a fashion that we can get good write speeds, better write speeds at lower cost. And we're not real engineers, so that this remains a little bit of a problem. Slide, please. So we can ask the question, with this best methodology, the optical method, we can ask the question of where do you go from here? And what we know is that mixtures of molecules is a good method of storing information. And I raise the point that's a really important point to understand, is that the way we get multiple colors or spots in a given location is to mix pre-made dyes out of a model and put a drop of that mixture on the plate. This is a lot easier than making a sequence-controlled polymer. So we work with molecules that are just mixtures, and you can take mixtures of anything that happens to be easily separable by the technology that you're using. Sequence and variation in DNA also works, and DNA has the advantage that you can provide replication, and you can make the DNA search, and you can do PCR-like things. I mean, there's a lot you can do with DNA that you can't do with chemistry. So it remains a little bit of a question as to which of these methods is the best method. But in terms of ease of doing things and ease of getting in, I think the business of just doing just doing mixtures is a lot easier than any other method. There are, however, given all of that, still reasons for looking at other new methods, and we are doing some of that as we go along. Slide, please. Now, a critical issue is what I've indicated here. Where do we stand in this methodology, and where do we go from here? Well, the thing that you can say is that this is a very versatile methodology. That is, you can work with mixtures rather than making a sequence-controlled polymer. And it's a very satisfactory way of storing information. It's competitive with DNA and with other methods that make sequence-controlled polymers, but we will make the argument that it's easier to make mixtures than it is to make polymers. Then the key issue is the one that's shown at this point. Who cares? And it's the question I ask of the graduate students repeatedly. When they come up with a new method, who cares about it? And I think it's fair to say that at this point, we haven't yet answered the question of exactly who cares. I'm going to show you just a possible list of areas of application, or mention a list of possible areas of application and commercialization. But I think commercialization is the key to this kind of thing, because let the market decide whether what you're coming up with answers the question or not. So, for example, this is a method that opens some doors in cryptography. And we have actually met with people who, come into the room and refuse to give their names. And you don't know where they come from. They can't, with the chance they're good, they are coming from a agency that deals with this kind of thing. So there may be something in crypto, or there may not be, but it's out of our expertise. I'd like to work with someone who knows about this. Patient records. In a patient record, you all are mostly young. So you have a cough, you have your chest x-ray done, and then you get better, or they give you antibiotics or whatever. But 20 or 30 years later, you come in with a persistent cough, and they'd really like to know, the doctors would really like to know if 20 years earlier you had a spot on your lungs. So they'd like to recover and look at your chest x-ray, but you want that to be private information. This is in principle a method of doing this. Whether it's better than existing methods remains to be seen. Movies take an enormous amount of information to store. So you make a movie and you spend a lot of money making a movie, and you know that 20 years from now, the movie that you've just made is going to become a classic and people want to see it again. How do you store that? And right now it's stored using magnetic tape and related things. So alternative methods that have the characteristic that you could read rapidly, write rapidly, read rapidly, and have long storage times look very attractive. And so that might turn out to be interesting. And what do people take images of right now? And the answer is apparently they take images of dogs and children, puppies and children. So you can take images of puppies and children just as well using this method as some other method, and it may be better for some purposes. So there are lots of places to look, but I can't say that we have yet resolved a methodology that has or uncovered a application that has an unambiguous plus in terms of this technology relative to other technologies. And you have to remember that magnetic tape and related things are extremely satisfactory, well worked out, well recognized by users for their strengths and weaknesses. And so it's going to be hard to get into this. Now, the next one, computation using information stored in molecules, is, I think, the hardest problem and the one that we would really like to have any good ideas. So we present you with a piece of glass or a silicon wafer that's been gold coated or whatever it might be. And we say, this has information on it. And what we would like to do is we would like to pick your operation. We'd like to do a fast Fourier transform on that, or we'd like to find out what image is stored, or we'd like to do something, but we'd like to change it. So we want to do a computation which changes the information stored on the molecule while it's stored, as I've showed you how to store it. We don't know how to do that now. We don't have a good method of doing it. And it's one of the real problems throughout computer science to come up with good methods of doing computation without taking information from storage, shifting it to active computation in the central processor, doing whatever you're going to do with it using computer code that's written there, and then shoving it back to storage location in a storage medium. And if any of you have ideas of how you would use information, I'm really open to argument. And I would particularly like to talk to people who are interested in number theory, since I think that this is primarily a number theoretic problem as opposed to other kinds of things. So then there's the question that we need to settle down and settle, which is how do DNA and mixtures of molecules compare as methods of storing information? And we just have to find that out. And it's fair to say that we don't, and other people don't really know how this is best done. So how do you tell about the storage, fidelity of storage over long periods of time? What experiments do you do to test this? The answer is we don't know. And then lifetime of different storage methods is the same sort of problem. So these are all, I think, the kinds of problems that magnetic tape faced early on, but it was against a background of existing technology, which was much thinner than it is now. And it's something which needs to be stored, needs to be considered carefully. If I had one problem to pick, I would have the problem of computation using information stored in molecules as being the most interesting one. How do we take information that's stored in terms of dyes and change the coding of the dyes while they're stored on a SAMS substrate? Slide, please. So what I'm beginning to feel at this point is suggested here, and that is that I'm convinced that this idea of storing information in mixtures is a very good idea, because there are so many mixtures that one can make without having to worry about reactivity or anything else, and which take advantage of technology developed for DNA or related areas, that it's a very attractive combination. Whether this method is available and better than DNA and its analogs remains to be seen. But part of the problem there is that we don't have clearly defined tests which indicate what better means. Then the key issue is the one that's shown in red in the center there. Who cares? For what applications does it make a difference what you're working with, and whether you're working with DNA or whether you're working with mixtures of molecules or whether you're doing something else? One application is going to be different applications. One answer is that different applications will require different areas of application of technology and different methods. Another is that we just have to work out a technology that has the characteristic that it does everything and it does it better than other methods. We'll see, I don't know. Computation, I've been through that, and I think it's a really key issue. How do DNA and mixtures of molecules compare as methods? That needs to be worked out. And then the lifetime of different storage methods, which is a part of a comparison of DNA and the methods that we've worked with, that has to be worked out. And all of these are legitimate scientific problems, but they work in areas like, for example, lifetime of different storage methods. Chemistry has never really faced this kind of problem before. And it's a very interesting problem to think about, but it's going to require some new approaches to come up with better ideas. Slide, please. And here are some of the people who've worked in this. It's been a mixed group. I would say that Amit has been the person who's primarily responsible for coming up with the optical methods. Michael Fink and Brian Cafferty, I give primary credit to the mass spec-based methods, but the person who developed all the technology that we used and who did most of the experimental work that we've touched on is Milan Merksic. And then Doug Richardson was in one of the laboratories at MIT and has been very helpful with optical methods. Alexei Ten worked with Milan for a while, and then after he graduated, he's worked with us. And he is a phenomenally good integrator of code and practical methods. And Sam Root falls in the category of being someone who's very clever about how to put things together. So it's been a relatively small group of people for a relatively large outcome, in my view. But the problem is not yet solved. It was supported by DARPA. And the trouble is that we are presently in a world in which both Russia and China, being countries where there is very, very good applied mathematics, we are also competing with them for the fabrication of next generation chips. And exactly understanding how to collaborate with such entities at present is a little bit unclear, and we've got to worry about how to do that. But I thank all of these people because they are the ones who've really made all this work. And it's very, 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 very satisfying to realize that a small group of people, 2, 4, 6, 7 people, including Milan, can get as much done as they got done in a couple of years. And I thank them, and I thank all of you for showing up. And I hope you found this an interesting way of thinking about this problem. Thank you very much, Cindy.
Great, thank you so much, George. This is a fascinating talk. I think there are a few questions and comments from the chat. Let's see. So the first one I see is from Alexander Swarsh. Are you still there? If you are, feel free to unmute yourself and ask your question or make your comment.
Hi, Cindy. Hi, George. Actually, I didn't have a question. What I posted to the group was rather a hint towards a startup that's pretty good in synthesizing DNA, not so much with their purpose in mind of creating a storage, but really unlocking some of the problems in biopharmaceuticals and so on. So they came up with a methodology to produce a couple of 10,000 base per long DNA in a completely automated way of synthesizing. So that seems to be a problem that many people have, and they seem to have come up with a solution to that.
I think that sort of application could well be the right direction to go. I am agnostic as to whether we go in DNA-based methods or whether we go in mixtures. The mixtures are simpler because I can take, for example, just fatty acids that I buy in kilogram quantities and put them in jugs and use them directly for this kind of chemistry, and it'll work fine. So the virtue of doing it with simple mixtures is that one is not limited by scale in any fashion. But in DNA and RNA, you have all the virtues of searching and amplification and other methods, which are really important and in principle extremely useful. And maybe that's useful as well, or useful in addition, or superior to, or something else. I'm willing to take any answer. At this point, we were interested in showing primarily that mixtures could be made to work really well and that were easy to do and gave effective results. And I think we've answered that question correctly, but we haven't answered the question of how one goes from there to something that is the most flexible possible method of doing things. So for someone who knows how to do the biological methods, I would be happy to work with you to see if we could figure out methods of going from there.
Terrific.
Thank you. And we have a question from Jan Korfink. If Jan, you're here, feel free to unmute. Okay, maybe Jan has logged out, but let me ask his question. He said, movie hasn't Pepperprint in Heidelberg been doing something similar for some time using peptide spots? I think the chap is called Frank Bratling.
Okay, I don't know it.
Okay.
So we need to look that up.
All right. So I noticed that it's already 9 minutes past the hour, and I want to be conscious of time. And I know a lot of people still have questions, but I just want to thank George again and all of you for being here at the seminars, and feel free to stay behind for a couple more minutes. And if George has time for a little more casual chat. Okay, thank you, everyone. Thank you, George, again for the wonderful talk.
Thank you for the invitation to give the talk, Cindy, and thank you all for showing up. And it's great to see your faces again and find that you're still alive. And I'm sure you're at least curious to find that I'm still alive, so that's a good thing to do.
Thank you, George. Still enjoyed.
Yep. Okay. Thank you. Thank you, Cindy.
Yeah, I think there are a few people who wanted to talk to you. If you still have a
All right,
couple
I'm
minutes.
here.
Yeah.
I'm here for, yeah.
Okay, great. Yeah. Oh, I see Chaobing is here.
But I saw Dong. I didn't see Xiaobing, but I wasn't perhaps focusing on the problem of seeing Xiaobing. He's normally fairly easy to see. Xiaobing, are you anywhere around?
Yes. So I'm
Oh, there you are. I see.
yeah. I'm tiny.
But you look very southern now. What you need is barbecue smeared on you, and an AR-15 on your back.
So George, for people who are still here, feel free to ask questions. But George, I have actually maybe a somewhat technical question. I'm surprised how the dyes are able to be read for so many times. Is it like, why is photo bleaching not an issue here? Like, or they photo bleach a little bit, but not as much as one would expect?
I think the answer to that is I don't know. But I think those dyes were chosen empirically because they didn't photo bleach in DNA work. So I think this is in part a example of, guided empiricism that has worked very well. But I think that the basic business of designing dyes and designing polymer coatings and reactive coupling systems and things of this sort is there's a lot of room, an opportunity for doing interesting and creative work there, but it would be helpful if we sort of had an idea of whether the focus should be on DNA or should be on dyes or should be on peptides of different molecular weight. I mean, you can find any number of different systems that will lead to distinguishable spots in terms of composition. And the question of which one is easiest and best, I don't know. I like the idea of mixtures. I like the idea of buying starting materials by the kilo and then doing relatively straightforward chemistry Michael Fink, who is next to you, has made a variety of really very interesting peptide-based systems, which rely on different fragmentation patterns in mass spectrometry. And that's yet another example of something that works quite well, offers real opportunity for multiplexing, and just hasn't been explored. What would make things easier is to have some indication of which of these different approaches is going to be most useful to the user and why, and then one could build around that specificity.
Great. Okay, so Dimitri Mostagas has a question. Dimitri, do you want to unmute and ask?
Sure, yeah. I was sorry if I missed this, George. In the talk, do you deposit a protective, a layer surface after you've done the dye printing?
You don't
And
have
is
to
that
do
part of the
that.
reason? Yeah.
I mean, these bonds are, after all, amide bonds, and they're really extremely stable. So the nice thing about doing just mixtures is if you choose the chemistry correctly, you do it without a lot of time and effort. You just mix things, and then you add something with another spot, and you're done, and everything takes care of itself. So it's an absolutely legitimate chemistry question, but the chemistry here can be designed to be as simple as possible, as opposed to being as labor intensive as possible, which is the way synthesis is often done.
I love it.
Great. I think Julia Vasakis has a question. Feel free to unmute.
Hi, George. Thanks for the great talk.
There you are.
So I'm curious to hear about increasing density of data per device, potentially by shrinking the spots or printing layers and then reading out the results in confocal. Yeah, just curious to hear.
There's a lot of room for some far out methods and then some near term methods. I think we've pretty well established that the best thing to do is to put the spots, make smaller spots and put them closer together.
Mm-hmm.
So I think that's a correct conclusion. But then there are other ways in which you can, in principle, increase information density by multiplexing in 3 dimensions and doing things of that sort. And we haven't done that much work with any of those methods.
Okay, and then my second question is about sort of the multiplexing and bit depth, potentially using some of the dyes like lanthanides or kind of other fluorophores. Do you think there's any sort of upper limit other than just kind of what can be read out spectrally on the bit depth here?
I'm sure there are limits, but there are things like, for example, quantum dots, which don't fade and which can be made extremely bright. And if you know how to do it, you can synthesize them in quantities, which would, I think, be very good alternatives. We have done just a little bit of work with quantum dots, and the little bit of work was not blindingly successful, so we haven't done that much with it. But I think for someone who knew how to do it, it would be a very good method and a very good thing to look at.
Great, thank you.
Michael, do you want to say anything?
No, I think you've captured it brilliantly, as usual.
Okay, this is Michael Fink, who is one of the people who has done really key work in this area. And I don't know, is Amit here somewhere? I didn't see that.
I haven't seen him, no.
Yeah, okay. So Michael and Alexei 10 have done most of the work with mass spec methods with Milan. And then some of the other work has been done by other people in the group, but I think our current supposition is that you get maximum flexibility with the mass spec method, but you probably get maximum utility in a data storage fashion with the optical methods because they're so fast and are so well tailored to take advantage of methods that have already been developed by the people who do DNA manipulations. Anything you want to say, Paul?
Paul, hi, first of all, and it is very good. It's very good to see you, number one. Number two, I would have hoped you would have said a word or two about microfluidics. I will say for my point,